In this tutorial, I'll go over the material generation aspect of the PuMA code. After the installation has been complete, PuMA can be opened by typing PuMA in any terminal window. To get to the material generation, open up the Domain Generation tab, which should be default open, and switch over to Generate Artificial Geometry. As you can see, there are 5 different artificial geometries that can be generated in this version of PuMA. The first, we'll start from the bottom, is just a simple cylinder. In the cylinder generation mode, type in the domain size in X, Y, and Z, the height of the cylinder, which if you wanted to span the entire cylinder can be an arbitrary height larger than the total domain. The cylinder radius, which in this case I'll put 75 voxels. The voxel length, which I'll leave at 1 micrometer. The direction of the cylinder, which I'll leave in the Z direction. And then if you want the cylinder to be hollow, check the hollow cylinder and then add a cylinder lumen, which in this case I'll put 25. Once you click Generate, the cylinder should be generated as shown here. If, for example, you wanted only a capillary and rather than an external cylinder as well, the cylinder radius, the outside cylinder radius, can be set to an arbitrarily large value, and then you're left with a box with a capillary through the center. The next generation module is the box. In this case, you input the X, Y, and Z domain size in voxels, the box length in voxels, and the box start position in voxels, as well as the voxel length. As you can see here, we're left with a cube of 100 cubed at the center of a 200 cubed domain. And to visualize the domain as well, you can launch an external visualization and you can see the box is shown as well. The third module is the sphere generation, which is somewhat similar to the box generation. Choosing a domain of 200 cubed with a sphere radius of 50, voxel length of 1, we can generate the sphere. The sphere can also be made hollow with some lumen, which can't be seen from the outside, but if you zoom in, you can see that there is a secondary sphere on the inside. The next option is to generate periodic spheres of a certain distance apart. So if, for example, we were to make a 400 cube box with a sphere radius of 20, make it periodic with 38 distance between the centers. You can see we're left with a periodic structure of spheres. This can also be inverted to create a simple foam-like material, as shown here. Which is just the periodic spheres that have been inverted such that the solid is the material not contained in the spheres. Moving on to the 2 slightly more complex domain generations that are possible, the packed sphere bed creates a random packed bed of spheres. If we make it 300 cubed with a radius of 15, plus or minus 5, voxel length of 1, and in this case we specify the porosity, we'll specify it at 0.7. In this case, there's also an option to invert it, but we'll leave it just as the spheres for this demonstration. And then an option as to whether or not to allow the spheres to intersect. If the spheres are not allowed to intersect, it will take longer to generate it, so we'll leave that checked for now. And as you can see, we're left with a packed sphere bed that has radiuses varying between 20 and 10 based on the plus or minus 15. If this is left to plus or minus 0, we'll be left with spheres of the identical radius. Moving on to the artificial carbon fiber preform. First, we specify the domain range in X, Y, and Z in voxels, the radius of each cylinder in voxels, and the delta, we'll leave that at 0. The length of each cylinder and the variation, we'll leave that at 0. And the angle variation. For a fully isotropic material, we have 90, 90, 90. For a transverse isotropic material, we can leave this at 15. If, for example, we wanted only cylinders in one direction, we could leave it at 0, 90, 0. In this case, I'll do a transverse isotropic material with plus or minus 15 degrees in the z direction. Finally, the voxel length and the porosity, which in this case I'll do 0.75. Similar to the packed sphere bed, you can allow the fibers to intersect or not. We'll leave that checked for now. As you can see, the operation is taking place in parallel and should be complete in a matter of seconds. And as you can see, what we're left with here is a carbon fiber preform with a preferential direction. I'll open this up in the full-size visualization. Which allows us to zoom in and see the details of the fibers. And that concludes the material generation aspect of the code.